Experiment 2, vectors. We are going to look at the different properties of vectors, look at adding vectors together, looking how to calculate their resultant, both graphically and analytically. So, oops, skipping around right here. We're going to do this remotely. So the first thing that you need to do is get some graph paper. I actually printed up some graph paper when I did this. I actually stole this graph paper from online. So you don't even have to go out and purchase graph paper, but you do need a protractor. You're also going to need a ruler to measurements. In any case, the first thing that they have you do is draw to scale right triangles with one of the angles equal to 30 degrees, 45 degrees, and 60 degrees. Measure the lengths of their sides, then using triangles and the definitions of trigonometric functions, calculate. You're going to do this using the measurements that you have and compare them to the calculated values of sine, cosine, and tangent for 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Present your results in the data table below. So what we want to do here is get your different values, A, B, C, D, E, and F, which represent the different sides of the triangle that we're going to see in just a little bit, and actually create two different tables, one for your experimental values and one for your analytical values. The percent error is how your measured values compare to your experimental values. So probably the easiest thing to do here, so you don't have to actually create three different tables, is create a table for your calculated, create a table for your experimental, and next to the experimental value, also write the percent error. Okay? So this is how we can do it. It's actually easy to do the 30 degree and the 60 degree on the same triangle because of the 30-60 degree triangle. Obviously we can't do 0 degrees, we can't do 90 degrees. And of course the 45 degree triangle is an isosceles right triangle. So you'll have no experimental values for 0 because there's no 0 degrees right triangles. You'll have no values for 90 degrees, okay? But I do want you to do the calculated values for them anyway. We know the sine of 0 degrees is 1, the cosine of 0 degrees, sine of 0 degrees is 0, cosine of 0 degrees is 1, tangent is sine divided by cosine, so that's 0, and you can do the same for 90 degrees. Okay, now, once again, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So for instance, when you're doing the 30 degree angle, okay, this is the opposite side, this is the hypotenuse, this is the adjacent side. For the 60 degree, D becomes your adjacent, okay, E becomes your opposite, and F still remains your hypotenuse. So, doing the calculations, measure the side, draw these triangles out, just like I've drawn these triangles out here. Use a protractor, make sure your angles are accurate, okay? And record these sides, A, B, C, D, E, F. You can put them in any order that you want. And that'll go back here. And from these values, okay, again for 30 degrees, D over F is going to give you sine. D is the opposite, F is the hypotenuse. E over F is going to give you cosine. E is adjacent, F is hypotenuse. D over E gives you the tangent of 30 degrees. Okay? Opposite over adjacent. So that gets your 30 degree measurements right there. Yeah, 45, that should say 45, by the way, folks. I'll make that correction. This is easy. You know, if you're doing the sine of 45, ignore that. Sine of 45 is A over C. Cosine of 45 is B over C. Tangent of 45 is A over B. Got the 60 degrees correct at least. And 60 degrees, opposite over hypotenuse is sine. Adjacent over hypotenuse is cosine. Tangent is opposite over adjacent. So that's part one. And again, when presenting the data, I would create two of these tables right here. One with your experimental values, one with your calculated values. Your calculated values are just plugging in sine, cosine, and tangent in from your calculators. Your experimental values are doing the ratios of these according to what their geometry is. Okay? Using these triangles right here. Okay, number two. 2A, you're drawing a vector. Again, you need a protractor, you need a measuring stick to do this. Given a vector with a magnitude of 5 meters, let's say that your graph paper is centimeter graph paper. I think this is really the best to use. Measure out 5 centimeters, because that's going to represent the 5 meters. You're going to do it at a 60-degree angle using your protractor. Okay? Graphically, what is AX? What is AY? Analytically, what is AX? What is AY? What is the percent error of your graphical calculation compared to your analytical calculation, where the analytical calculation becomes your accepted value? Okay? Again, if we split this up, the x component looks like this, the y component looks like this. Clearly, we can see how far x goes. And again, you can actually do this measurement. 1 centimeter, 2 centimeters, a little bit more than that. Do the same for y. Get those values recorded and plug in numbers. 5 meters times a cosine of 60 degrees, 5 meters times a sine of 60 degrees, and then these become your comparisons. Okay? So again, AX, AY, you're resolving this vector graphically. AX, AY, you're resolving this vector analytically. That's 2A. 2B, given two vectors with magnitudes 2. Excuse me. I'm not going to do a whole new video because I sneezed. A is equal to 2, B is equal to 2 also. So these are going to be 2 centimeter long vectors on the scale if you choose it. A makes a 30-degree angle. So use a protractor from the origin, go 30 degrees from your reference line, and I get A. Now you're adding vectors, so you're going to do a head-to-tail method right here. B doesn't start at A. I mean, I guess you could do it if you use the parallelogram, but head-to-tail is probably easier for this. Okay? So B, I'm going to start where A stopped, and instead it's going to go 120 degrees. Okay? Again, the reference line is sitting right here. So 90 degrees would be straight up, 120 degrees is 30 degrees past that vertical. So again, use your protractor. C is A plus B. Determine what CX is graphically, what CY is graphically. Okay? And then using the equations, you're going to calculate, determine graphically. You can actually just measure with the meter stick. But use a protractor to measure the angle. Okay? Analytically, it's a little more complicated. Analytically, break it into the AX and AY components, the BX and BY components. The X components of C are AX plus BX. The Y components of C are AY plus BY. Once you have the X and Y components, Pythagorean's theorem gives you the length of the vector. Inverse tangent gives you the angle. So those values, the analytical values, get put in there from doing all these calculations right here. And again, percent error for C, percent error for the angle. C, you're going to add 3 vectors. A, B, and C. A is at a 30-degree angle. It's 4 meters long, 4 centimeters on your graph paper. B is at a 90-degree angle. Notice it goes straight up. Here's a reference line, 90 degrees. Okay? That is 5 meters long. And C is 6 meters long, 6 centimeters to scale, at 225 degrees. So our reference line here is for C. That's 0 degrees. 90 degrees is straight up. 180 is here. So 225 represents 45 degrees from 180 degrees. So here I've drawn all these vectors graphically. Find out the x and the y components of D analytically, just like you did the last time. Again, measure the length of D. What is the angle that it makes? By the way, folks, I purposely, well, don't use my drawings to do this lab. Draw your own stuff because you have to show these. My drawings are just estimates. They may be right, they may not be right. So again, graphical D, theta D, analytical D, theta D. So graphical, how long is this? What angle does it make? It looks like it's a little past 90 degrees. Analytical, now you've got to do all the x and y components of it, A, B, and C. You add all the x components to the x components, all the y components to the y components. The length of the vector is the square root of the x component squared plus the y component squared. The angle is the inverse tangent of dy divided by dx. Last one. Define the opposite of a vector. There's another vector of the same magnitude but pointing in the opposite direction. Given two vectors with a magnitude 2 meters and 2 meters at 45 and 135 degrees respectively, find the magnitude and direction of C such that A plus B plus C equals 0. Okay? What that means is this plus this plus this takes me back to the origin. If this were displacement, it would take me back to where I started and there would be 0 displacement. So the way that we do this is when we add vectors, AX plus BX plus CX has to equal 0. AY plus BY plus CY has to equal 0. Okay? Again, you can measure the length of this vector, determine its angle, okay, and also compare that analytically. All right? And again, to the A vector, B vector, C, because it's the opposite of A plus B, is negative AX minus BX. CY is negative AY minus BY. And again, to get the length of C, to get the angle of C, you can fill that in the analytical. Okay? So once again, you're going to do percent error for all the things in C. Your accepted value is always, the actual value is always the analytical here. Your experimental for this is the graphical. Okay?